Well, hello everyone. Today's an exciting day of chemistry. We're going to start a new unit, Unit 1, the structure of matter, and we're going to focus on lesson 1 today. So if you'll turn to your study guides, open it up to lesson 1. We'll start looking at some new chemistry principles and concepts. So here we go. All right, everyone should be to lesson 1, matter. We're going to focus our attention on the question of understanding what matter is today and how we classify matter. And we're going to look at elements and we're going to look at compounds. I'm going to show you various examples of elements and compounds. We're just going to have a lot of fun here. All right. So in your study guides, as usual, take really good notes. And then go back and study those notes and study this video, relook at it if you need to. Okay, so here we go. The study of matter. Now, chemistry is often referred to by definition is the study of matter and energy and how matter, different parts of matter interacts with one another and how energy and matter are related to one another. All right. But we're going to focus on matter in this lesson. So by definition, matter is anything that has mass and takes up space or has volume. So space and volume mean virtually the same thing. So what we're looking at is anything that has mass and volume is considered matter. Examples of matter. You are matter. You have mass and you certainly have volume, take up space. Desks, tables, trees, cars, pencils, your study guide, the computer. I mean, we can go on and on and on. All of these complex material things around us are all considered pieces of matter based on the fact that they have mass and volume. All right, so matter can actually be classified. We can break it down into essentially two major classification categories, okay? So here we have matter overall, and matter can be broken down into pure substances, or they can be broken down into mixtures. So matter either comes as a pure substance or as a mixture. Now, pure substances themselves can be broken down into compounds and elements. Okay. So when you think of what a pure substance might be, it's either an element or a compound. Whereas a mixture, on the other hand, which can be classified into two categories, homogeneous or heterogeneous, those are a combination of multiple pieces of matter. They could be a combination of multiple compounds, such as water and oil, or water and salt or sugar. Or it could be a mixture of or combination of elements. Could be like hydrogen and oxygen mixed together. All right. The idea of a pure substance is that it's exactly what it says. It's pure. It's one type of element. It's gold elements or silver elements. Okay. There's no mixture involved. Or it's a pure compound, like pure salt or something like that. And so that's the way you can kind of think of pure substances. So again, a pure substance is either an element or a compound, and a mixture is multiple component parts or pieces that are put together and are interacting with one another. And they can be either homogeneous or heterogeneous. All right. In this lecture, lesson 1, we are going to really focus on pure substances, elements and compounds. And then in lesson 2, we will focus on the other big category, mixtures, and look at homogeneous and heterogeneous mixtures. But that's not until lesson 2. So for now, let's focus on the all-important pure substances and the two classified areas of pure substances, elements, and compounds. All right, now for right now, the way I would like you to visualize what elements are and their proper function in matter is to think of them as more or less building blocks, okay? Elements are considered the building blocks of all matter and materials. So much like the alphabet is the building blocks of words, and we take various letters in the alphabet and combine them to form complex words. They could be very short words, they could be very long words, but the alphabet, those are building blocks to words, our language. Well, elements are the building blocks to complex pieces of matter. And what we can do is take these various amounts of elements and combine them, either a few of them or many of them in different ways, to create more complex pieces of matter, like you and me, like the chair that you're sitting at, your computer, your cell phone, a table, something like that, okay? But it all begins with these elements, these building blocks. Now, I have a variety of building blocks with elements, such as sodium and chlorine. So you can think of these two, the element sodium, okay, and the element chlorine. And basically what's going to happen is these two elements are going to come together, and they're going to chemically bind to one another and to begin to form more complex pieces of matter. In this case, it's going to develop salt. And let me show you kind of what salt would look like when we build or put these elements together, these building blocks. And you would have something like this. This is a salt, sodium chloride crystals that we see here, all right? All built because we combined the elements sodium and chlorine, okay? We'll look at that a little bit more later, right? So again, think of all of these, think of the elements simply as building blocks. We link them together and we create more complex structures of matter, right? Now, by definition though, a little bit more scientific definition, we can think of that an element is a substance, okay, is a substance that cannot, and this is important, cannot be broken down or destroyed by normal chemical reactions, all right? So once an element is made, it cannot be broken, it cannot be destroyed by everyday chemical processes. Now, don't be confused with chemical processes or chemical reactions with nuclear type of reactions. Now, nuclear types of reactions have the ability to do that, to break down and destroy elements, all right? But those are not everyday processes that we usually encounter or deal with, all right? Most of the processes that we encounter happen to be chemical processes or chemical reactions. And so kind of keep that in mind for right now, okay? Now, every element, each element is essentially made up of a specific type of atom. And we'll kind of explore atoms in more detail a little bit later on, but elements are essentially made up of atoms, okay? Now, there are currently 118 different elements, And most of them are naturally occurring, 92 of them to be exact, that we would find not only on planet Earth, but throughout the universe, 92 of them. The rest of the elements are synthetic. They are made by us in a laboratory setting using sophisticated equipment, essentially, okay? But 118 known elements, 92 of them are naturally occurring, okay? All right, now, elements, it's important to understand that all elements have a specific name to them, all right? And here's a few examples. We have silver, we have potassium, and we have Einsteinium. Now, every element that has a name also has a corresponding symbol to it. For instance, silver has the symbol Ag, and potassium is K, and Einsteinium is Es. Now, you'll notice that the first letter in the symbol is always capitalized, okay? Now, that's important to remember, okay? If there's a second letter in the symbol, then it will be lowercase, like we see with silver. The A is capitalized, and then the G is a lowercase. Potassium only has one letter in the symbol, so it's capital K. And then Einsteinium with two letters, the first one E capitalized, followed by the lowercase s. Okay, it will become very important that you learn the names of the elements and their symbols. And so we will be practicing that often, learning these elemental names and symbols. And again, there's 118 elements with proper names and proper symbols. Okay, and it's well. Let's move on from here. Let's go on. I think you get the idea. All right, so where do we find a list of all of these elements that we find, all 118? Well, most of you already know that we find these elements on a table called the periodic table of elements. And as this table represents, this periodic table, you can see all 118 elements. And notice that I find this always interesting is that these elements are in blocks. Remember, the elements are the building blocks. And so each element is in a specific block in the periodic table. The first element that we see up here is hydrogen, given the symbol of capital H. And the second element, which is way over here, is helium, which has the symbol He, capital H, lowercase e, okay? And then we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Many of these you are familiar with or have heard of before. So if we ever need to know where the elements are and a list of them, we can always turn to the periodic table. And as I mentioned before, it's going to be very important that you learn the element names and symbols on the periodic table. Okay. Now, the other thing I really want you to know, and sometimes we get this this thought that that the elements are just these words with symbols on some kind of table, but they are real. They are real things. They are real material objects, and they have unique characteristics about each one. And I've listed some pictures of some of these elements on the table, like strontium and what strontium looks like, and gold and mercury and copper and sulfur, phosphorus, and carbon, okay? So they are real things, and I have some samples of elements here that I'm going to show you. So here is a sample of copper, and the symbol for copper is Cu, and of course the color of copper comes from the elemental color of copper, okay? No big surprise there. But you can see that copper has some really cool crystal structural patterns here, right? And we see that with many solid elements as they form a crystal structure. This is one of my favorite crystal structures of an element. This is bismuth. Looks really awesome. It looks like those pyramids that we see down in ancient Central America and so forth, like the Aztecs and so forth, and what they made, these ruins. Okay, so this is a really elemental bismuth in its crystal structure. Right, really cool. All right, sulfur. Sulfur is an element. You can see a block of sulfur here. Right, it also forms a crystal, and the crystal structure of sulfur looks better in the picture here than it is here, because this is a big block of sulfur like this. But some elements at room temperature, and those are all, oh, let me show you this because I like this one. This is europium right here. And I store europium in this glass tube here, essentially because europium is really reactive with oxygen, and so it oxidizes the europium really fast, and so basically you lose the purity of the element, and so basically there's no oxygen inside of this glass tube. Instead, there's basically an inert gas that's non-reactive to the europium to preserve it, okay? But europium is really cool. You don't come across it very often because it's rare. It's one of the rare earth metals. It's actually located in the periodic table down here. Europium right there, symbol UE, and yes, it is named after the continent Europe, okay, where it was discovered, okay. But it's really cool, right? But those are all solids. I'll come back to that. So they're all solids at room temperature, though. But there are liquid elements at room temperature. One I have right with me right now is bromine. Okay, so bromine is liquid at room temperature. And it looks kind of like a rustic, reddish brown liquid at room temperature. You can kind of see it's also in this vial to keep it stored, falling out. Okay, but my point is to show you these elements is that they are real, and it is these particular elements that are the building blocks that come together to form more complex structures of matter. And the elements themselves can be very useful. They're also worth a lot of money. Some of these elements are super expensive. This one is actually $1. This is a silver dollar because it's made out of pure silver right here. So this is worth way more than a regular paper dollar because it is all made out of silver. It's really, you can kind of see it, it's really cool, pure silver, silver dollar. So these elements are also have a lot of value, worth to it. And we mine it and we sell them, and so that we can make various types of materials or use it even in our coins, okay, and so forth. All right, so hope that makes sense as far as elements are concerned, that they are the real deal. All right. let's move on. All right, so here's a periodic table. I know this is not in your notes, this periodic table, but this is a famous table mapped after Theodore Gray's famous periodic table that he put together an element collection. But the reason why I like this table is because it shows you some of the pictures of what these elements look like, and also some of the useful ideas of these elements. Some elements we don't have actually images of because they don't last very long. So we have the images of some of the people that they're named after and so forth. Okay. All right, so let's get into the other type of pure substance. So we looked at elements. Again, elements are the building blocks of matter. They can't be broken down. They can't be destroyed through chemical reactions or processes. All right. So when we string elements together to create more complex structures, we can create what are known as compounds. Now, by definition, a compound is made up of two or more elements in a fixed ratio. Now, that's an important part of the definition. In a fixed ratio, and can be broken down into pure elements. Okay, so now elements can't be broken down by chemical reactions or chemical processes, but compounds can. And compounds can be broken down into the pure elements. So I lost my sodium chloride, but essentially we take those building blocks that we have, we break them down into the pure elements, and then we have those pure substances. But we also can then combine them together to form complex compounds. So if you look here as an example, a compound represented by chemical formulas, okay? And we will often use this term chemical formulas as we represent a compound. Essentially, a chemical formula is usually made up of the symbols of the elements that are involved in making the compound. So if we were going to create this compound called copper oxide, it's a combination of the element copper and the element oxygen, and we combine them together to form copper oxide. And it is represented by the chemical formula CuO. Cu is the elemental symbol for copper, and oxygen is the elemental symbol, or O is the elemental symbol for oxygen. Okay, let's give you some more examples, but keep in mind of this term fixed ratio. Okay, it's a ratio between these atoms. For instance, in this case, the fixed ratio between copper and oxygen is 1:1, and I'll get into more of that in just a minute. Okay, so here's our building blocks. Again, remember that essentially we look at the elements as a block. Okay, block on the periodic table. And so what we're going to do is we're going to take this copper, again, the symbol is Cu, and we're going to combine it. That's what the addition sign means. We're going to combine it with oxygen, and essentially that combination is going to make the compound copper oxide. And you can see that it looks like a powder black at room temperature with the chemical formula of CO. Okay, now the ratio is what's important. The ratio here is represented by 1 copper and 1 oxygen. So therefore the ratio is 1 copper to 1 oxygen. And we usually represent the ratio as subscripts in the formula. But since they're both 1:1, we usually do not show the ones in the formula. Okay, so we can get rid of those ones there, but you just have to remember that it is a 1-to-1 ratio. But I mean, the other thing to point out here is that copper looks so much different from copper oxide. I mean, I showed you, go back and I'll show you again, that essentially copper is this crystal structure, this hard solid metal that we're familiar with. And then we take oxygen. Now, oxygen at room temperature is a gas, and you can't see it. It's clear, it's invisible to us as a gas. This picture shows you oxygen in its liquid form. When oxygen is in its liquid form, it actually is a pale blue color, as we see here in this picture, all right? So when we combine copper and oxygen, they look very different from the end result of copper oxide. And that's true. The properties of copper are way different than the properties of oxygen. And then combining copper and oxygen together create even different properties than the original elements that it's made up of. And that's characteristic of all compounds. They have very different properties than the elements that make up that particular compound. And please keep that in mind. That's really important. In fact, is you probably want to write that down, is the properties of the compound are very different than the properties of the individual elements that make up that compound, okay? All right, so let's take a look at some other examples here of compounds. Right, so here what we're going to do is take the element hydrogen, and we are going to combine it with the element oxygen, and in doing so we create water. Now you will notice that the ratio is 2 to 1, okay, because there's a 1 really after that O. And so water is a 2 to 1 ratio of 2 hydrogens to 1 oxygens. And that's where we're talking about in the definition of that, the fixed ratio. Water will always come as 2 hydrogens to 1 oxygen. All right, and that ratio is fixed and will not change. And these ratios and these compounds are super important. We're going to spend a lot of time discussing these ratios in the compound and using them, okay, for various things. But again, hydrogen is one of those building blocks. It is an element. And when we take hydrogen, it looks very different than oxygen, and the properties are very different from one another, and we form water out of these two elements. And water is such a vital compound on our planet, such a vital compound to life, to you and me. And so it's kind of fascinating to me that we take these elements that are so different from one another, put them together, and creates a marvelous molecule or compound of water and the ability of what water can do. I mean, hydrogen itself, it's explosive. I mean, it's flammable. It will blow up. And oxygen, well, it's an element that's needed to make something burn in the first place. And you put two of these two together and you create a compound that actually puts out fires. I mean, it's so amazing to me. It's incredible when you think about what we can do with all of these elements and the compounds that we can make. An endless, I mean, it's an endless number of possible compounds. And so we can create all sorts of more complex pieces of matter for our benefit, for our needs. And so I think it's pretty fascinating in that regards. Okay, so don't forget, I think most of you know that water comes in a 2 to 1 ratio, and so forth. Okay, so let's look at one more example here, I believe. So here, wow, we're going to take 3 elements, okay? we're going to take 3 elements. Now, these elements we saw earlier, hydrogen and oxygen, but now we're going to introduce carbon into this. And carbon, it's a black solid at room temperature. It comes in different forms called allotropes. One of the forms of carbon is diamonds. All diamonds are made up of carbon. And so in other words, a diamond is just elemental carbon. Okay, that's all it is, elemental carbon in a specific structure. And so we take elemental carbon and we add it to hydrogen and we add it to oxygen and we create the all important molecule sugar, all right, which we all love sugar. I don't know anyone that doesn't like sugar, okay? We use sugar for so many things to sweeten our food and so forth. But you'll notice that sugar, it forms a basic ratio of 6 carbons to 12 hydrogens to 6 oxygens. So we have a 6 to 12 to 6 ratio. And that ratio is fixed for sugar. So we often look at sugar as C6H12O6, all right? So again, sugar has quite a bit different properties and different look than the other 3 elements that make it up. Diamonds, if you ever tasted a diamond before, it certainly is not sweet to the taste. It may be sweet to the look. They're pretty cool looking, but they don't taste very good. Trust me on that. Hydrogen and oxygen, they don't really have a taste at all. But that sweet sugar is awfully good when we make those combinations. All right? All right, so don't forget that. The fixed ratios are an important part of the definition of a compound. A compound, again, is made up of 2 or more elements that combine in a fixed ratio. They can be broken down. We can take sugar and we can certainly break it down back into oxygen, hydrogen, and carbon. Okay, so that is definitely possible to do. All right, so our last thing we're going to look at today is what we call particle models. Now, particle models are really important because we're going to use them a lot in chemistry to help us to explain how matter looks and how it works and interacts with other pieces of matter. Now, we can't see elements, we can't see compounds with our eyes, or at least single elements or single compounds. We have to get a large quantity of elements in order to begin to see them with our eyes. And so often what we use is visualize particle models to represent elements and compounds at the very small microscopic level, or even really submicroscopic. I mean, it is really down there at a very small level. Okay, so what are some things that we need to know about these particle models? I'll show you what they look like in just a moment. But models, all models, in fact, in science are just theories. Okay, and a theory is basically something that tries to explain the behavior of matter, why it acts the way it does. Okay, so whenever you think of a model, I want you to think of it as that it is just a theory. It is what we believe is going on. It is a way, again, to say this is how we think that matter is behaving, how it's working at a particle level, at a very small level. Okay, so we can use particle models to represent all particles, to represent atoms, to represent molecules and compounds. Okay, again, all at this particle level or molecular level. Okay, the molecular level or the particle level is really, really small. Okay, super, super small, much smaller than the level of cells and everything else. You can't use a microscope, a normal microscope that you use in biology to see the molecular level. Okay, well, that just doesn't work. So we're barely getting special microscopes, these electron scanning microscopes, where we can even begin to look at the surface of atoms and compounds. So for the most part, we just don't have a good way of visually seeing them at such a small level. So we build models instead. Okay, so we're going to work with models a lot, just so you know. Okay. All right, so let's look at some examples of particle models. We have two of them here. All right. These models are just representing elements. This one here is representing the element sulfur, which is indicated by its symbol. And this one is represented by the element iron, okay, because of its symbol. So we have iron and sulfur. Now, because iron and sulfur are in these circles, and usually we represent our elements in circles. They don't have to be, they could be in any shape. They could be triangles, they could be squares or whatever, but usually they're going to be its own single particle unit. And they can also be various colors, like this one is kind of shaded gray, the other one is white, and so forth. So different ways of representing these elements in these particle models, okay? Because the iron and the sulfur are not in contact with one another, I would assume that these elements are separate from one another, and they're not forming any compounds. So this would be an example of pure sulfur and pure iron that are mixed together in a mixture. So in reality, this is a particle model of a mixture and not of a pure substance, because we have both iron and sulfur. Okay. Now over here though, notice that the iron and sulfur are now like next to each other where they're almost connected. And so here what we're saying is that this is a whole unit, or one single particle, the iron and the sulfur, and that would represent a compound then, okay, in this particle model. Okay, each one of those. It represents that the iron and the sulfur have combined together these two building blocks to form a more complex structure called iron sulfide. Okay, and you can see that. All right. One thing I'd like to do before we're done here is look at some real compounds for a moment. I have some various compounds that I want to show you. So I've already showed you this one. This is salt, or what we call chemically sodium chloride. And because it is made up of sodium atoms and chlorine atoms, okay, they create these cool crystal structures. They almost look cube structure like here. So that's salt, or sodium chloride. Now here's a really interesting compound looking crystal. I'm going to be really careful with this because it's very delicate. Okay, these crystals are way cool if you want to take a look at these. This compound is made up of the element antimony and the element sulfur. So we combine antimony and sulfur together, and we get essentially antimony sulfide, which is really cool compound, right? Very, very delicate compound, okay? So I'm gonna be really gentle with that. And here's the last one I'll show you. Cool little crystal patterns, this green. Sometimes they're actually purple crystals with this particular compound. This is made up of calcium and fluorine, all right? So calcium, the element calcium, the element fluorine combine to form what we call calcium fluoride, okay? Calcium fluoride, and it makes these beautiful crystals, okay? So anyway, we look closer. All right. So anyway, I just wanted to give you an opportunity to see what some of these compounds look like before we sign off here. All right. So back to particle models. Just to conclude, we will be using particle models a lot to represent the behavior of matter at the molecular level. So get used to drawing them. Also on the AP and IB exam, particle models are used quite a bit in problems, and so you need to be able to interpret them very well. All right, I think I got one more thing I want to show you. Let's erase all of this. So these are also models. We have a model of oxygen, we have a model of water, carbon dioxide, so forth and so forth. And the different colors you see are different atoms or elements that make up these particular compounds. Like these two represent oxygens, two oxygens to form O2, which is oxygen, okay? And then this is water here, which is oxygen, and then these white ones are hydrogen atoms, and that gives us our ratio of 2 hydrogens to 1 oxygen. This carbon dioxide, that's a carbon atom, and these are 2 oxygens here, and then so forth and so forth. So we can use different colors, again, to represent different atoms, and these models are called space filling models. We will use and talk about space filling models, and essentially they just show the connectivity of the atoms together. Notice that the hydrogen and oxygen atoms are connected to both, the hydrogen is connected to the oxygen, but the hydrogens are not connected to each other in water and so forth. So it just kind of shows that. So again, these are particle models. To represent individual compounds or molecules in this case. And we will use these space filling models as representations of matter as we go, okay? So, I mean, that's it for this lesson, lesson 1. I covered a lot, but there's a lot of important things that you need to be aware of. So please take the opportunity to review your notes, to relook at this video if you need to. And really, that's it for now. So we'll see you later. Have a good day.